Hi everyone, this is Pratima Naik. Today, in this video, we'll discuss some Ncert questions of class 12 mathematics based on relations. Question 1. Relation R in the set A 1, 2, 3 up to 14 is defined as R is equal to x, y such that 3x minus y is equal to 0. Determine whether the following relation is reflexive, symmetric and transitive. Now, relation R is not reflexive as x is never equal to 3 times of x. So, x comma x does not belong to the relation for all x belongs to set A, because we cannot write that 1 is equal to 3 times of 1. Relation R is not symmetric as if y is equal to 3 times of x, this does not mean that x is equal to 3 times of y. For example, if x is equal to 2, y is equal to 6. 6 is equal to 3 times of 2, but 2 is not equal to 3 times of 6. So, if x comma y belongs to R, y comma x does not belong to R. For all x, y belongs to set A. So, it is not symmetric. Now, relation R is not transitive. If y is equal to 3 times of x, z is equal to 3 times of y, then y is not equal to 3 times of x here. For example, x is equal to 1 and y is equal to 3. 3 is equal to 3 times of 1. Z is equal to 9. 9 is equal to 3 times of 3. But 9 is not equal to 3 times of 1. So, xy belongs to R. Yz belongs to R. But xz does not belong to R. So, the relation is neither reflexive nor symmetric nor transitive. Next question. Relation R in the set of integer defined as R is equal to order pairs of x comma y such that x minus y is an integer. Determine whether the following relation is reflexive, symmetric and transitive. Now, let us come to the solution. Relation R is reflexive as x minus x is equal to 0, which is always an integer. So, x comma x belongs to relation for all x belongs to set of integer. Now, relation R is symmetric. If x minus y is an integer, this implies that y minus x is also an integer. So, if x comma y belongs to R, this implies that y comma x also belongs to R. For all x comma y belongs to set of integer. Now, relation R is also transitive. If x minus y is m1 an integer and y minus z is also an integer m2, then x minus z, we have to prove that it is an integer that can be written as x minus y plus y minus z, that is m1 plus m2, and which is equal to, let it be m, and sum of two integers is always an integer, so it is true for x minus z. So if x comma y belongs to R, y comma z belongs to R, this implies that x comma z also belongs to R. For all x, y, z belongs to set of integer. So it is reflexive. So that the relation R in the set of R of real numbers defined as R is equal to order pairs of a comma b such that a is less than equal to b square is neither reflexive nor symmetric nor transitive. Now the answer is Relation R is not reflexive as x cannot be written as equal to x square for all x belongs to set of real numbers. We know that 2 is not equal to 2 square. So x comma x does not belong to R for x belongs to real number. Relation R is not symmetric. If x is equal to y square, this does not mean that y is equal to x square. For example, 4 is equal to 2 square, but 2 is not equal to 4 square. So if x comma y belongs to R, y comma x does not belong to R for all x comma y belongs to set of real number. Now R is not transitive. If x is equal to y square, y is equal to z square, this does not mean that x is equal to z square. For example, 16 is square of 4, 4 is square of 2, but 16 is not equal to square of 2. So if x comma y belongs to R, y comma z belongs to R, but x comma z does not belong to the relation for all x comma y comma z belongs to set of real numbers. So it is neither reflexive nor symmetric nor transitive. If R1 and R2 are equivalence relations in a set A, so that intersection of R1 and R2 is also an equivalence relation. R1 and R2 are equivalence relation defined on set A. So we will take a order pairs A comma A. This belongs to R1 as well as it belongs to R2 for all A belongs to set A. This implies that A comma A belongs to R1 intersection R2 for all A belongs to set A, showing that R1 intersection R2 is reflexive. Next, A comma B belongs to R1 intersection R2 implies that A comma B belongs to R1 and A comma B belongs to R2. This implies that B comma A also belongs to R1 and B comma A also belongs to R2. This implies that B comma A belongs to R1 intersection R2. Hence, R1 intersection R2 is symmetric. Similarly, A comma B belongs to R1 intersection R2. B comma C belongs to R1 intersection R2. This implies that A comma C belongs to R1 and A comma C also belongs to R2. This implies that A comma C belongs to R1 intersection R2. This shows R1 intersection R2 is transitive. Thus, R1 intersection R2 is an equivalence relation. Let R be a relation in set A of order pairs of positive integers defined by order pair x comma y related to order pair u comma v if and only if x plus v is equal to y plus u. Show that R is an equivalence relation. Now solution. Clearly x comma y related to x comma y for all x comma y belongs to set A. Since x plus y is equal to y plus x. This shows that R is reflexive. Further, x comma y related to u comma v, this implies that x plus v is equal to y plus u. This implies that u plus y is equal to v plus x. and u comma v related to x comma y. This was that R is symmetric. Similarly, x comma y related to u comma v and u comma v related to a comma b. This implies that x plus v is equal to y plus u and u plus v is equal to v plus a. Now adding them will get x plus v plus u plus b is equal to y plus u plus v plus a. Or this implies x plus b is equal to y plus a. Hence we are getting x comma y related to a comma b. Thus R is transitive. So R is an equivalence relation.